Donut Lab just released their first independent test results for their solid-state battery, and buried in the data is something no one's talking about. This particular test talks about fast charging, and in this data, there's actually quite a bit we can learn from this cell. So in this video, we're going to talk about what this test proves, what it doesn't, and what we know so far. I'm Ricky, this is Stupid Da Vinci. This video is brought to you by Outskill. Quick context on who did the testing. VTT is Finland's largest state-owned research organization with about 2,400 employees. A legit lab with legit equipment, and the data is trustworthy. But here's what most people are missing. VTT is not a certification authority like UL, for example. They actually sold that arm of their business in 2018. What VTT does is run customer-directed tests at their discretion. So Donut Lab chose what to test, and VTT executed it and provided results. Now, before we get into the numbers, it's worth understanding why Donut chose to test this particularly, because this isn't just about fast charging. It's about two of the biggest engineering nightmares when it comes to solid-state batteries: pressure and heat. Most solid-state batteries need 20 to 50 atmospheres of external pressure just to work properly. That's because the solid-state cell doesn't have liquid electrolytes flowing into every nook and cranny. You have to have solid surfaces pressed against each other to have great contact. And if those contact interfaces aren't perfect, the ions can't flow very well and the performance dies off. And then there's swelling. We did a video with QuantumScape recently where they showed how they get around this. They have a flex cell because the pack will change size about 20% because it's an anode-less material, right? So the lithium is plating on the anode. So there's a swelling that has to be accounted for. None of that happens here. So then the purpose of this test is to show OEMs, people who would actually buy their cells to put in cars and motorcycles, that this battery is going to be really easy to implement. Stay tuned to the end because I'll tell you exactly how. Before we get to the data, let's just talk quickly about how battery testing actually works. VTT used the PEC ATC 0550. It's an industry standard battery cycling machine made in Belgium. It has 80 channels and it's lab grade in terms of its precision. And here's the critical thing. This machine is completely chemistry agnostic. It doesn't know or care what's inside. In this test, it uses constant current mode. The machine pushes a fixed current, say 286 amps, and the voltage does whatever the cell's chemistry dictates. The machine doesn't choose the voltage. It basically measures it. Think about it like this. Let's say you're building a machine to test how strong you are at arm wrestling, okay? What I'm going to do is build a machine that allows you to win at 1 millimeter per second. So I want to fix how quickly your arm comes down. Now, how much force I have to apply to prevent you from going any faster or slower, that's variable, right? So the goal is a nice linear movement of your arm from top to bottom. A really, really strong person might require a lot of force, and then they get tired very quickly, and then it gets easier by the end. Maybe me, I'm really weak, but more consistent. I use more flexor muscles. I might have something like this where it's not that easy, but I can hold my power longer. That variation in power to keep that single speed is what this machine is doing. It is maintaining a current that is constant, regardless of whatever voltage it has to do to push it through the battery, right? Traditionally, batteries' voltage will go up because the voltage has to increase to be able to push more ions through and charge that pack. This, in a way, produces a signature. It's like that slope for the arm wrestler. You could tell who's who, a really strong person, a weaker person. It has this signature. For example, if this were a capacitor, you'd see a straight line. If this is a sodium-ion battery, the voltage would plateau around 3 volts or so. If this were LFP, you'd see a flat line around 3.2. Instead, what VTT recorded is a curve that climbs from around 2.9 volts through a plateau around 3.6 to 3.8, then slopes up to 4.3, which is textbook for a NMC lithium-ion battery. Once the voltage hits 4.3, the machine switches to constant voltage mode. It clamps the voltage to 4.3 volts and lets the current taper down naturally until the cell is full. By that point, the fingerprint is pretty much on the page. So when I tell you the voltage profile matches NMC lithium-ion, that's not because VTT programmed it to look that way or it was a limitation of the test equipment. That's just not how the machine works. The machine is completely agnostic of whatever it's charging, and it can handle pretty much any chemistry or any type of battery. By embracing innovation and bleeding-edge technology, the Dutch seemingly did the impossible. And the bleeding edge of tech today is AI. And if you're curious or unsure how to get started with AI, our sponsor this week, Outskill, has you covered. Outskill is hosting a free 2-day AI mastermind training this Saturday and Sunday, 16 hours of hands-on learning, and right now you can grab a seat completely free. A guy won $1 million by creating an AI film using Google's VO3. And I'm actually using AI coding to build a new website for home energy usage and insights. I can't wait to show you more soon. AI isn't coming, it's here. And the gap between people using it and ignoring it is getting wider fast. Forbes just reported that employees using AI at work earn 40% more than those who don't. You'll learn how to build AI agents that do meaningful tasks, automate workflows across tools like Notion and Google Sheets, and connect systems that keep running while you're not at your desk. People who've gone through this training have built services that generate significant income. I used to tell people that the idea was 20% and the other 80% was execution. But now with AI, curiosity and ideas have never been more powerful. So if you're curious about practical ways AI can help you build things, attend both days of OutSkill's AI Mastermind to get premium lifetime bonuses like the AI Prompt Bible, the AI Profit Roadmap, and your personalized AI Toolkit Builder. With over 10 million learners and a 4.9 out of 5 score on Trustpilot, OutSkill is a resource I think you're going to love. Use my links to reserve your spot today. Huge thanks to OutSkill and you. Now back to the show. In their test, they use a passive aluminum block for cooling. In some of the tests, they have 2 blocks, top and bottom sandwiched, and others just 1 for cooling. There's no passive cooling. There's no fans or water pumps or water blocks. It's just an aluminum radiator that is sandwiched between the cell. And also, if you look here, one of my original gripes with their first testing was that the wires feeding in 100 and 200 amps of electricity just wasn't sufficient. Look at the tabs and the size of the wire in these tests. This is VTT. This is a legit testing agency, and they've got that definitely nailed down. Now let's walk through exactly how VTT structured this, because the methodology matters just as much as the result. They ran 7 tests on a single cell, the same one throughout, and they start slow on purpose. The cell is a 26 amp hour pouch rated at 94 watt hours of capacity at a 3.6 volt nominal level. Test 1. VTT charges the cell at just 24 amps. That's a gentle 1C charge rate. 1C means it could charge or discharge a battery in 1 hour, using constant current at up to 4.15 volts. Then they held it at that voltage until the current trickled down to 1.2 amps. This is standard charging, discharging textbook procedures. Nothing here is special anyway. They then let the cell rest for an hour and discharged it at 24 amps in the same way for a full cycle. Charge up and charge down. So here it is, right? They ramp up the current and charge it all the way till trickle charges, the battery gets to full, and then they let it rest for a while, and then they discharge it. And they did this twice. So they charged it, discharged it, charged it, discharged it. The point is to establish exactly how much capacity the cell actually has before you stress it. The answer, 26.1 amp hours and 91 watt hours. Right on spec, exactly what Donut said it was. Test 2. Now VTT sandwiched the cell between 2 passive aluminum heat sinks. This is the best case cooling for this particular test. And then they started testing at 5C, 5 times faster than before. They slammed 130 amps into the cell using constant current up to 4.3 volts, then held voltage until the full 26 amp hours were delivered. After 1 hour of rest, they discharged at 1C to see what came back. The result, 26 amp hours out, 100% capacity recovery, peak temperatures around 47 degrees, and a full charge in 13 minutes and 33 seconds. Then they went to 11C. This is really fast charging, 286 amps through that pouch, which is a crazy number to think going through a single pouch. That's not something that cars today are doing. There are companies like CATL that are working on batteries that can charge at this speed, but they need crazy active cooling systems to take that heat out of the pouch. Same protocol, constant current 4.3 volts, then constant voltage to fill it up. The cell went from 0 to 80% in 4 minutes and 53 seconds. Full charge in 8 minutes flat, peaking at 63 degrees. Afterward, 99.6 of the capacity was recoverable. 25.9 amp hours came back out. That difference, that 0.2 amp hours is what is lost as heat when you charge batteries faster. But that result is pretty crazy. Now for test 4, they switched to 1 heat sink underneath the cell, but nothing on top for less cooling. More realistic of how cells actually sit in a pack, right? Because if you have pouch and pouch and pouch, typically you cool on one side. So this is a little more indicative. They ran another gentle 1C reference cycle to re-baseline and make sure the cell was still healthy after that blast abusive test. And it was. Actually, the cell delivered 26.5 amp hours, slightly more than the initial test, but it's right on track. There's been no degradation. The battery cell is safe. Test 5, 130 amps again, but now with less cooling. Full charge in 12 minutes and 15 seconds, over a minute faster than with 2 heat sinks. It's actually faster charging with less cooling. Peak temperatures hit 61.5 degrees versus 47 before, and 100 capacity recovered again, 26 amp hours when discharged. Now, here's where it gets interesting. The cell charged faster with worse cooling. And this wasn't a fluke. The same pattern showed up with every C rate, either 5 or 11. The reason is that higher temperatures lowered the cell's internal resistance. You can actually see the voltage curves. The charging voltage drops with one heatsink, meaning less resistance across the cell. The cell actually likes to be hot. Test 6 and 7 are 11 Cs with one heatsink, the real stress test. VTT pushed 286 amps, same as before, with minimal cooling, just one plate. The first attempt hit VTT's 90-degree safety cutoff, which is a lab constraint, not the cell's constraint, but VTT has a requirement that if a cell in testing reaches 90 degrees Celsius, they have to shut it off for safety. They cool the cell for 4 minutes, then restrapped it tighter. You can see in this video that they actually have some clamps, just like woodworking clamps to hold it in. This is not 50 atmospheres of pressure. It's just to make sure there's good contact, again, from the interface of the heatsink to the pouch. This time it peaked at 89 degrees, just barely under the safety limit. 0 to 80% in 4 minutes and 36 seconds. Full charge in 7 minutes and 18. That's 17 seconds faster to 80% and 39 seconds faster to a full charge than with 2 heat sinks. So the cell performs better with less cooling. For a conventional lithium-ion cell, wanting to be hotter is completely backwards. Heat means degradation, electrolyte breakdown, and shorter life. You cool these cells as aggressively as possible. But here, performance improves with temperature. It's also consistent with pseudocapacitive titanium oxide systems where ion kinetics speed up with heat. We'll get back to this, which was my original theory, was that it was a pseudocapacitor. We'll see. I went through the VTT data and calculated something I haven't seen anyone else publish: the round-trip efficiency at each C charge rate. At 1C, about 91 watt-hours came out versus 101 going in, which gives you roughly 90% efficiency. At 5C, that drops to about 85%. And 11C, it's around 82%. That 18% there, that's the heat, right? If the cell is getting hot, that energy is lost somewhere. I theorize that this could be a pseudocapacitor, and the efficiency numbers challenge that theory. A pseudocapacitive device stores energy through flat surface reactions with inherently low internal resistance. So you'd expect 95 to 99% efficiency, right? Static energy versus chemical energy storage. The 90% at 1C is actually on the low end, even for regular lithium ion, which typically hits 92 to 95%, and it's nowhere near supercapacitor territory. Now that you understand how the test equipment works, this becomes the most important clue in the entire report. The VTT test used a 4.3 volt charge cutoff, 2.7 volt discharge, and 3.6 volt nominal. Remember, VTT's machine doesn't choose those voltages. That's the function of the end product being tested. If you put the voltage profile next to known chemistries, it's almost identical to NMC, nickel, manganese, cobalt, lithium-ion batteries. But this voltage response fingerprint isn't actually all that we have. Using that same data, we can actually gather one more piece of information, which is the internal resistance. Since the test machine pushes a fixed current and the cell produces a voltage, we can use Ohm's law across all 3 rates, right? Remember, there's 3 tests. There's a nominal 28 amp test, the higher 130 amp test, and then the full 286 amp test. So we have 3 data points that we can look at. 2 things jump out. First, all 3 values, we just picked some random data points here. All 3 values land between 1.3 and 1.9 milliohms, which is squarely in the range of what you'd expect from a liquid electrolyte NMC battery. A solid-state electrolyte would typically show higher resistance because ions move slower through a solid than a liquid. Second, the resistance actually drops at higher C rates, 1.9 milliohms of resistance at 5C down to just 1.3 at 11C. And that's because the cell is hotter at higher rates, and the lower resistance at higher temperature is exactly what we'd already knew we'd expect from the data. So the math internally checks out. So not only is the fingerprint that of a lithium-ion battery, like an NMC battery, the internal resistance based on the reports that they've provided match up with a liquid electrolyte NMC battery, not even a solid state. And this is where I find this uncomfortable, because I met with the team and they told me there's no lithium in this cell. And all the data that we have so far points to there being lithium in the cell. Now, maybe they've come up with some new crazy thing we've never heard of or something. I don't know. And if you're wondering, why didn't VTT rip it apart and give us a full report of what's inside? Remember that Donut is their customer, and their customer asked them for something in particular, and that's exactly what they did. It is not their job to disprove or to get to the bottom. They're not investigative journalists. They're an engineering firm that does this kind of testing for battery cells, and they provided what Donut asked for, which is what we would expect, right? That's not We'll have to wait to see the rest of it, but I can't for the life of me imagine why you would lie about this, because as soon as that cell hits the market, we're going to know what we need to know. Finally, I want to add one more piece of information, which is the cell that we saw at CES was like 123 watt hour, which if we used, we don't know the weight of the packs, we can't get exact numbers, but they were claiming 400 watt hours per kilogram. And so if we back solve, that would be around 310, 315 grams is what the pouch would weigh. And the cell that they tested is only 98 watt hours. That difference from 98 to 120 something watt hours drops the battery's energy density down to like very high-end lithium-ion batteries, but nothing crazy, right? We don't have 400 watt hour per kilogram lithium-ion batteries. This could just be that these are all prototype cells and they're all different sizes, and maybe it weighs 250 grams and not 300. We don't know, right? These are just speculations. I'm trying not to do that too much, but what we do know is that, man, that fingerprint looks really, really familiar. Between starting filming for this and making this video, one of my friends, Ryan, who runs a channel called Zeroff, made a video about this as well. And he mentioned that there might actually be some swelling. And I went back and looked, and there is a little bulge. Again, it's hard to quantify, and it could be like time of day or lighting and different things. But the pack does appear to swell a little. We'll show you the video here. But clearly it's not under pressure. And that would only really matter when you go from one cell to like a module with 50 of them and to a pack that has thousands of them, right? These kinds of things are hard to quantify at this point. What they're telling you here is not giving you data to figure out what the chemistry is. I think that will come later. What this is a signal to every OEM that the challenges that you're thinking about going to a solid state architecture for your cars is not going to be a problem. What are the challenges? Needing 50 atmospheres of pressure, basically having like a hydraulic squeeze to keep these batteries in contact. Because without the liquid electrolyte and a jelly roll, you need contacts that are really, really strong at the interfaces. That isn't going to be a problem. And with charge speeds that you don't have to worry too much about cooling. So if you just have like bottom plate, or, if you just do like plate cooling or run ribbons, whatever you're doing now, it will be sufficient for their system as well. A couple things that they haven't touched on is the 100,000 cycle life. That will be another test. They'll have to test very quickly over and over for months and months. Maybe they've got a cell running right now and they'll share data when it comes out. So we can't corroborate that. All we have is about 7 or 8 cycles for that one cell from this one company. The second thing is the 400 watt hours per kilogram energy density rating. We can't figure that out either. Now, again, it would be easy enough. They had the cell, they could weigh it, they could check the measurements and stuff, and they could have told us the actual density, but that's not what VTT is doing, right? They're here at the behest of Donut to test exactly what they're asking for. And their test was fast charging and cooling. And they've given us quite a bit to look at now. This report shows us the fingerprint, the charge curve for voltage and constant current testing, which is amazing. That's really good information to have. Unfortunately, it really looks like a standard chemistry. That's what I'm seeing so far. It's hard to explain why that would be at this point. But call me the optimist. I don't know. Maybe there's something else they're going to show us. I don't know. At this point, though, it doesn't seem that revolutionary. It seems like a really good battery, by the way. Can I just say, if all the other claims of what they've got here are true, this is a great battery. Like, it's a battery that people would want to put in their EVs. Is it a game-changing, mission accomplished mic drop moment? No, not at all. It's like an evolutionary improvement, right? Maybe we're closer to 300 watt hours per kilogram with this battery, and maybe something about it has better charge characteristics or something. I don't know. What do you think? What have I missed, right? Like, I try to dig into this as much as I could. What did I miss? What do you guys know? Sound off the comments below. We can start a conversation. And when more news breaks, we'll cover it. All right. I'm Vinci. Thank you so much for watching.